No, I didn't see. Do you see the share screen yet? No, I don't think. Yeah. Give me a minute. I try to pop it. Where is that? I try to pop it. Hold on. Okay. So do you see that? Guys, do you see that? See the screen?
Yeah.
Yes.
Okay, cool. So last time, can you see see the moving of the mouse? Can you? Can you see the moving of the mouse? Okay, sure. Yeah. Last time we just mentioned the AR2. So the AR is a linear since when we take the first derivative epsilon t with respect to phi 1 and phi 2. Hold on, I just turned off the line. I'm sorry. So I need to turn off the line. Hold on. So alrighty, back to the slide. So understandable, the AR2 can be estimated through the linear least square. So it is let me see, I want to pop. Share screen. So the AR belongs to the linear model. So I cannot type. Strange. So. No. So how can I back to the now how can I return back to the share screen? Strange. I don't know how to turn it back. Share screen. No, I don't see. No. Once I return back, okay, sure. Okay, then stupid. That's really stupid. So we cannot simultaneously show the shear and the control panel of the teams. Okay, so it must be it can be estimated through the ordinary linear least square estimation method. Then, so in general, the AR ARIMA P00 or PDQ. So AR2 model can be written as this. So this is the format in the matrix form for ARIMA. Then it can be estimated through the least square estimation methodology for sure. So when we look at the offline estimation about the moving average, like this is as simple as the simple one. So when we take the partial the first derivative, the epsilon t. This is the error term respect to the unknown parameter. Finally, what do you find, guys? What do you find? Actually, we take the first derivative of the function, still the function of the parameter itself, the theta. So then, which is a form of linearity. So in this case, it cannot be estimated by using the ordinary least square method. It must be estimated by the nonlinear estimation method. So I show you, there's a textbook. Hold on. Yeah, let me show you. Yeah, this is a textbook. That's why I always expect you to have to print it out. Pretend to your Marquardt. Hold on, Marquardt, M-I-N. Mastrangelo. Hold on, M-A-D. So we don't have any Marquardt. Will. Mastrangelo. Okay, hold on. I go to the web. I go to the web to find the related. Can you see the screen?
Yes.
Okay. Nonlinear least square. Nonlinear square and Marquardt Levenberg algorithm. Yeah, this one. It's a Marquardt Levenberg. No, not this one. Let me search. Okay, this is a this is a Levenberg Marquardt algorithm. Okay, let me show this English version. Okay. So in mathematics and computing, Levenberg Marquardt algorithm, known as the damped least square method. So damped, that means this is a nonlinear least square, which is typically used to solve nonlinear least square estimation problems. So I'm going to copy the link to this. Yeah, hold on. I copied. Okay. Now I copy the link to the control panel of the team. So it can be recorded. Okay, then which is available. So once you would like to understand what is the difference between linear estimation and nonlinear estimation, it is totally accessible. This is totally accessible. Okay, so yeah, this is important. So we're going to have a test next week. So we're going to have a test next week. Is that going to be included in the test? So you need to understand the difference between the linear model and the nonlinear model. All right. So offline estimation alternative only. So you can see that the minimum mean square error using the nonlinear optimization. I mentioned that the Levenberg Marquardt. Which can be typically used, or there's a package in Python or package in MATLAB. This is this is everywhere, so it can be accessible this without any problem. So alternative, like we can solve it by linearization of the model, or the main purpose of the offline estimation is to estimate the unknown parameter mu and sigma epsilon square, like this. I think we mentioned this last week. Okay. And this is offline estimation. So offline versus online. So the difference going to be, yeah, let me see that. The least square method we have seen is an offline method since for the time series cases we deal typically collect the data offline. So that means like a design of experiments, like a regression analysis, or even though we fit in the model by using the machine learning, or we fit the model by the convolutional neural network. Since we collect the data first, then the fit an empirical model. In here, we fit the empirical model by using the Box and Jenkins model, like ARIMA. So this is called the offline. Then online. So online, that means we fit the model as the data is generated. So once while the data comes into the system, or which was recorded as a reading from the system, then that is so data collected real time. Then that can be accessible by the computing algorithm online that going to be used as the feedback or feed forward for the system for the control purpose or for the monitoring purpose. So that is called the online method. The online method, yeah, there's a quite famous example like extreme control, like self-tuning control, the PID control, EWMA, MV, this is known as a minimum variance control. So I think the PID we have mentioned in the class. So then we move to the section 3.8 right here. Hold on, 3.8. It's like this. Do you see the screen of the textbook? Jin, can you see the textbook I share through the screen? Can you?
No. No.
No.
No? Geez, hold on. No, I would like to. Okay, hold. No. You see this, right?
I only see the slides.
The slides. Okay, I'd like to show. Hold on. Yeah, that's why I don't like Jesus. Hold on, give me a minute. Give me a minute. Okay. You only see the slide. Okay. Okay, so then you see this, right? You see the slide, right?
Yes.
佩珍，你可以看到我分享的 PPT 吗？现在？
可以，可以。
可以 ，OK， 好。Then I would like to share the textbook. Hold on. Yeah, give me a minute. Give me a minute. Okay. No, it doesn't show this. Why? Why can't I? Hold on, why can't I show my... Yeah, hold on. I share. I just turn it off and share once again. Yeah. Hold on. I need to pop. Okay. So. And yeah, you can see this, right? Now, right?
Yeah,
Yes.
I can see.
Okay. So now we move on to, that's so strange. I need to toggle between different screen. Okay. I can toggle. So this example, we already uploaded data to the line group. So as a whole, we're gonna submit by Wednesday for sure. There's no problem. And okay, 3.8. So we move to 3.8, 3.7 of PDQ. Okay, the diagnosis checking in the time series data. So this is a quite usual. It is not only says Minitab is also in Minitab. There's also available in Minitab SAS is called a June box peer statistics. So this is called a Q statistic. The statistic is a portmanteau. Portmanteau, that means the full package test, which is a null hypothesis, alternative hypothesis saying the row I starting all the correlation are equal to 0 for k, I equal to 1, 2, 3, 4, k. So evidently larger the values of Q are due to the larger autocorrelation, then which will lead to the rejection, the null hypothesis. If the Q is so big, or the significance level is so small, then we're going to reject the null hypothesis. So the rejection rule is to use if the Q statistics is greater than the critical value like this one, or the p-value is very small, like 0.01%, 0.0005, and so on and so forth. Okay, so then we're back to the, no. Okay, do you see the PPT? Yes, I think, right? Yes. Do you see the PPT yet?
Yes.
Yeah.
Okay, done. So the residual should be Y sequence or Y noises if the model fit a statistical algorithm. If let me tell you, if the model is not adequate, then the residual will not be following Y sequence. So as long as you find your residual doesn't follow Y noise, then you better think to redo your modeling. So that means, you may neglect some important parameter, or the order of the model you apply may not be sufficiently complicated for your data. So Q statistic is a portmanteau test for the data. Okay. So this is a Q statistic that is used to test the autocorrelation are equal to 0 or not. So then you need to check the level of the significance. So in the next week we might give you a data. So we're going to since it's only 2 hours, so you need to bring your computer. Hold on. Also, so you're going to separate. Next week going to 2 hour in-class test. Then you just write it. I'm going to send my question by Word file to every one of you. Then you fill in all your answer in the Word, and you just transform into the PDF and send it back to me within 2 hours. Okay, so it may accommodate 70 points of the test. The remaining 30 points of the test going to be take home. I give you the data, so you're going to fit the model like this ARIMA. You follow the procedure stated in the textbook. So I give you the data, then you can return your fitting result and experimentation in interpretability within 24 hours back to me. So I think that's going to be the midterm exam. It's going to have to separate it gets separated into two portions, two parts. First part is in class. You're going to finish it within 2 hours, and the second part going to be take home. However, you need to kick it back to me within 24 hours. So if use of the residual, so residual is an indicator to tell if the model is adequate or not. So if the residual show the structure, hold on, let me. If the residual shows structure fit, so we're going to fit the ARIMA, fit on the ARMA PQ. I'm sorry. Okay, I just add some note for residual. If the residual shows structure, any structure, so we need to fit. So we need to fit our ARMA PQ for residual. So to residual like this one, this is ET is a residual. So residual going to fit a separate ARMA. We'll put an E in this the subscript. This is different. This is different from the original A polynomial. So this is A polynomial, C polynomial for the residual, like this, the ET. So then we incorporate this model back into the original time series model given by this. Original we only have this, right? So no AE and CE, since yeah, the residual is not white sequence, which is color. So we need to put it back into the model. So it turned out to AE, and the difference, the number of the different data, and C, CE, and the epsilon T. In here, epsilon T gotta be C, epsilon T gotta be white sequence. Got to be white sequence. Since we already fit the residual, which show structure by using its own ARMA model to remove those color structure. So I'm sorry. So the epsilon need to be following, excuse me, need to be following Y, WHIT. Yeah, do you see the text I typing? Can you see that, guys?
Yes.
Okay, cool.
Yes.
So okay, then we back to the slide. So I need to toggle since the too many things I need to. I'm sorry. Okay, now I toggle back to here. No, the SAS is too expensive. We don't want to use SAS. No, too expensive. this is a server client structure for every user. For one semester, going to cost university about $100 per semester. So this is too expensive. So for fitting this, okay, we toggle back to the control panel. So I suggest you using some Minitab. Minitab this is okay, or MATLAB is okay as well. Or Python. This is some Python packets catch, or scikit-learn. The scikit-learn. Okay. Then so this is only when I was in the other university, the SAS package is available. Okay, then time series approach to SBC of autocorrelated data. So some authors, that means this is researcher. Okay, I just as a have proposed that if there is an inherent autocorrelation in the data, the autocorrelation corresponding to the inline state. So that means, so yeah, it existing. So we need to live with it. That means there's never ever any approaches we were able to get rid of it. So that means we need to, well, the autocorrelation is not possible. We like to use APC or the automatic process control, or EPC engineering process control for compensation. So that's the best we can do. So in this approach, special cost will be suspected where a residual of the fitted ARIMA model fall outside the control limit. So yeah, this is quite difficult sometimes. In this case, if the autocorrelation in that data is inherent or of essence, then we still claim the process is in control state. So for this perspective, a special cost will be, well, suspected where a residual of the fitted model for outside the control. So in such a case, we like to use the Schuhart chart, EWMA or Q-SUN chart for hold on, to monitor the residual instead of monitoring the mean and the standard deviation. So they called the residual chart. The residual chart. This is quite famous. Okay, let's toggle back to the slide down. So then recall that the residual is defined as the YT minus YT hat. We put a caret on the top. That means it is estimate or forecast. So which need to follow the Y sequence. So they can be monitored using an SBC chart. Problem 1, the process changes do not show easily in the residual. The problem number 2, if the time series data is non-stationary, the concept of the ship makes no sense. So yeah, this is the two major problems we need to work with. So that's why we always like to use an EPC online in order to compensate for the autocorrelation or drifting effect. That is inherent for manufacturing environment. So other approaches sample less often. So we do not sample that often, since sample less often going to so where let me just put some notes. Where the autocorrelation decreases, the information is lost. Yeah, this is a problem. So if we sample the data less often, that means we, for example, originally we sample the data like a sample every 10 minutes, one sample every 10 minutes. If we just change our sampling plan, we sample the data once every 2 hours. So that means the autocorrelation definitely reduces and autocorrelation decreases by information is lost. So going to use a variable control chart on the original data. Yeah, it could be. It could be. Or yeah, this is published in the journal quality. Yeah, let me put on here. So on the original data, or if can be, or yeah, let me put. Or alternatively, it can be regulated by manipulating some other controllable variable. Yes, controllable variables. Using the EPC approach, EPC's engineering control. Yeah, do you see my typing? Do you? Yes or no? Hey guys.
No.
Yes.
Okay.
No.
No.
No, no.
No. I mean, do you see the screen? I just typing. Change to the engineering process control in here. Do you see the mouse moving?
Oh, yeah.
Okay.
Yes.
Okay. Sure. Thank you. Okay. Okay. Then back to 3.10. So going to toggle back to the textbook. Yeah. Do you see the screen of the textbook?
Yes.
Okay. Thank you. I'm going to review that. Okay, before we doing that, we're going to see this example. Okay, please use 1 minute, 2 minutes. Read the example 3.18. I'm going to review this example. No, maybe this is way too long. Give you 5 minutes. I'll be back. I'll be back in 5 minutes. Understand? Read example 3.18. 5 minutes. Get it? Answer me, please.
Yes.
Yes.
Okay, thank you. 5 minutes. Okay, have you finished? Have you finished? Okay, let's go back to the example. So this is a Riemann analysis for the viscosity data in another book, Montgomery book, using the SAS procedure or a Riemann input file simply as follow. So only first, fourth, and the last observation are shown. So this is a card. The reading, the input data, and well, so we directly see the output. So look at this. This is viscosity data, and we'd like to see the. So it showed the working series, the mean standard deviation, number of observations, totally 100. So you can see that this is autocorrelation data. It is it is more, yeah, it is more monotone decreasing. Hello, are you back? So are you back? Then this is inverse. This is inverse autocorrelation. The partial inverse autocorrelation, or inverse autocorrelation. The partial autocorrelation is either two spike cuts off. So this is check for Y sequence for the lag 6, degree of freedom, lag 12. Then this autocorrelation. This is degree of freedom, and so 1, 2, 3, 4, 5, 6. Then the chi-square. This is chi-square. This is the June. This is yeah. Let me show you this. The test statistic. The June Box-Pierce test. Here, this is the June Box-Pierce test. Showed up here. This is significant to the lag, the chi-square. This autocorrelation. So then let me see that chi-square equal freedom probability less than chi-square, something like this. This is autocorrelation. Let me see that. Okay, the conditional least square estimation for the mu. This is the psi. The AR1 0.7, the AR2 minus 0.4 is right here. One spike, positive, negative. So this is AR2, the AR2. Then we see the approximate probability significant level for according to the t statistics. The t-value is quite big. Quite big. The 3 so significant. So the 3 need to be incorporated into the model. So constant going to 20.125. So so the AIC, SIC totally residual. This is yeah, this is called the goodness of fit test statistic. Test the statistic of the goodness of fit. Something like that. Test the statistic of the goodness of fit. Then we see another. So like probability autocorrelation 1. So it's totally to like 6 chi-square, and chi-square from to like 6, 1 to 6, 7 to 12. So the 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, 7, 8, 9, 10, 11, 12, and so on and so forth. So it lists all of that probability chi-square. Yeah. Is non-significant. So this is in here we should check maybe 2, 2. So the probability greater than chi-square 4, 10, 16, 22. Yeah, it's going to show all the possible k for your perusal. So this is the autocorrelation plot of the residual. If we use AR2, then yeah. 0, this 0, of course, this if the k equal to 0, so the autocorrelation got to be 100%, 1.0. So remaining, you can see that all so fitting that is within the upper control limit and lower control limit. So got to be 2 divided by square root of n. So this is the upper bound and lower bound, the 2 standard deviation. So yeah, this is quite good. Finally, we have, yeah, let me see that. Finally, based upon this, we're going to reach a conclusion. Do we have it? Show below 13. So in here, a Riemann model, we identify variable, so estimate p equal to 2. That means this is AR2. So p equal to PDQ, p equal to 2. So if p equal to 2 is specified, then we can see that the autocorrelation show no structure and show only Y sequence, So it is it assigned the AR2 model is a statistical fit to the data we have. So then look at the figure 3.29, the general approach for monitor autocorrelate data using a Riemann model. And when the data autocorrelate data into the modeling block by feeding the ARIMA PDQ model. So yeah, if the residual E1, E2, E3 uncorrelate, if model is okay, then we just stop. Then we stop. If the E1, E2, E3, they are correlated, what we're going to do? We're going to fit. So if it is not true, we're going to fit this. Hold on. Hold on. Jesus. I'm going to AEC. Yeah. If it's not true, then hold on. Do you see that? We're going to fit. This is the residual. If the residual are not white, we're going to fit ARMA model to the residual, and we can obtain AE and CE. AE and CE right here, and incorporate into original time series model. Then, so then we're going to fit the ARMA model to the residual. This is another block here, and if the corresponding filter, the residual, found to be uncorrelated, then traditional SPC chart can be applied. Can be differentiated between the common or random causes and special causes. So yeah, like this. Okay. Here's some chart problem. Okay, then back to the slide. Okay, then from this slide on. So time series approach to the SPC of the autocorrelated data. So in here, if the output is Y sequence, no, the residual Y sequence, we can construct the SPC for monitor YT for sure. And if there's some control or some rule has been set up, if the output is quite away from the specification, then going to feedback the control mechanism, then going to feedback to the XT. So try to manipulate or try to tweak level of XT a little bit in order to bring the process back control. So going to address this in chapter 5. Okay. So this is 2 o'clock. We have a break. So I'll be back. So please, guys, return to the control panel. Return to the class in 2:10. See you later. Hey, 佩珍，你们这样子，那个线上看得清楚吗？
看得清楚。
什么？
看得清楚。
哦，你们声音怎么那么小声呢？
看得清楚。
OK， 就是我这个画面这样有看到吗？
可以。
然后这个 PowerPoint 这样可以吗？
可以。
然后这个这样可以啊？
可以。
OK， 好 ，OK， 谢谢。 Hey guys, we're back here. We're back here. Yeah. So, let me see that this is some cases. Are you guys back?
Yeah.
Yes.
Okay. Yeah. So the number will be increasing for sure since the pandemic, since the problem of Taiwan now is the lack of vaccine. The lack of vaccine. So, so actually, there's so the problem need to solve by the government. So otherwise, we don't have anything to deal with that. We need to wait until Taiwan self-made vaccine. The vaccine will be available until the end of June. I think it should be no earlier than late June. So going to have our vaccine. So once everybody is vaccinated, then the community vaccination going to get into effect. At that time, the infection, so that virus will not be that infectious that much at that time. At least this is down to lower than 30% of infection. At that time, then we came back to our life came back to normal. I believe. So in the meantime, so we need to sustain. We need to live up by ourselves. So please always be face mask when you go out. Yeah, this is the first priority, and do not think it is so trivial. So don't want to do that. Be sure to be face mask when you go out, and use to clean your hands once while you have some contact with some paper or pens or some computer not under your control. When you back into your home or back into your room, please try to sterilize. No, not fertilize your both hand. I think that will be the second. This is second top priority. And stay away from trouble. Not go to the places that are too crowded, and just as try to get your lunch or dinner as a takeout as fast as you can. And I think, yeah, this is the best we can do. So just go to online class and get a lunchbox and stay home, read the paper, prepare the homework, prepare the examination. I think this is the best you can do. The best you can do. Yeah, get it? Jun, since you are the foreign student, yeah, it's kind of difficult for you to live in Taipei City. Jun,
Yeah.
yeah, do you understand? So
Yeah, I can
so
understand.
try to, as easy as can be. Just you can stay at lab since the lab is quite spacey. Then after study you can return home. So where do you live? You live in
In
dorm?
dormitory.
Okay, cool. So you just walk back to dorm and get the lunch box, get the dinner box, and back to your room. That's it.
Yeah.
And prepare. Uh, always use your soap to clean your both hand. I think this is the best we can do, right? And
Okay.
And how about the supply of the mask? Do you have some backup?
Yeah.
Okay.
Yeah, I have a sufficient mass.
Okay. 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 Let's go back to the slide. Okay. Now we move to the chapter 4. So this is this is a kind of a different style of the chapter. So called the transfer function model. So this slide shows the dynamic system. This is the input. This is the output, and the tree. This is a black box, and the noises and the noise come from the top. Let's check the. Hold on. Chapter 4. The transfer function modeling, like this. So this is dynamic system, dynamic process. The description of transfer function system. So it is supposed that we can observe pairs of variable, the xt and yt at the adjustment point or interval. Yeah, in time for t equal to the t starting 0, 1 to the adjustment point. I mean, so this is a control. So I would say that this is timing for control, or timing. I'm sorry, timing for manipulation. So when we like to perform control. So that is when will we like to have control. So if xt is fixed at the constant level, okay, and we stop here for a while since back to here. So we're going to have a midterm exam next week from 9 to 11, 2 hours in class. So you cannot bring your computer. No computer, no textbook. No. Open book and open notes. No computer, no cell phone, and no laptop, no desktop, no pad. You can bring your calculator, your stationery, and your pencil, and something like that. 2 hour in-class test. So you can bring all the book you can have. Is there any question? We're going to cover from chapter 1 to chapter 3. Is there any question? So going to X one by one. Pei Zhen, are you clear about the examination? Hello? Yeah, hold on. No. Let me explain that. Do not go to school. Do not go to school. Do not go to the classroom. You stay at home. I'm going to send my exam in Word to, I'm going to send it to Line so you can download the Word file. 这样清楚吗，佩珍？ Hello?
哦，清楚清楚。
Okay, so gonna send it to the line group. You download it, you just type in, or you can print out by yourself. So you can print out and use a pencil to write your answer on the paper. Whatever you like. You can type it or you can use a pencil to write it. Is that clear? Jun, Jun, are you clear?
Yes.
Okay, then Go away. Are you clear?
Yes.
Okay, then Xiangyu, you going to have a test or not? 项羽，你要考试吗？项羽。
应该不会吧？
Okay, then John, are you clear?
Yes.
Okay, are you clear?
Yes.
Then we're going to. You only have 2 hours, so you can use you can write your answer on the paper. If you write it, just write on the paper, or you type in the paper. Then, when you finish, you transform into a PDF and send your test back to me by email. In PDF. So send. Hold on. Gonna send your test in PDF back to me by email. Is that clear, everybody?
Yes.
Yes.
Okay, cool. Oh, let me type it. Yeah, this is my email. Then it won't matter you write your answer or you type your answer. Be sure you can use your cell phone to take no. However, this is only 2 hours, so you just transform back to your test into PDF and send your PDF back to me. That's it. That's it. That's it. So it's just okay. This is the ASIC code. Well, you cannot use it. However. So I hope you can sit in the. So well. I will monitor how you answer the questions. So you need to turn on your video. So you need to turn on the voices and turn on your video. I can see you. Is that clear?
Okay.
So you need to turn on your video. So let me see. How can you just fill in? How can you answer those questions? So it's just easy. You just sit in front of the desk and turn the video always on. You just write it down. Just write your answer. Then I can monitor to your to the video, right? Okay, I hope you can get my point. Let me ask all of you. I think Junzong, you understand what I'm talking about, right?
Yes.
And do you understand? So gonna turn the video on to see how you answer those questions, right?
Oh,
And Sanghao, do you understand?
Yes.
Okay, Pei Zhen, do you understand?
Yes.
So you need to turn on the video and go. Do you understand? Turn on the video. Let me see how you answer those questions. That's it.
Yes.
Okay, cool. Let's go back to the slide. Then, so if x is a fixed constant, let the x and y will be eventually reach a steady state. That's called equilibrium. equilibrium. Value denoted by using, yeah, just search a little bit. The y infinity. Equilibrium in Chinese, we call 平衡, right? In Chinese, equilibrium called 平衡, yes. Yeah, so then the steady state, this equilibrium relationship between the input and output is usually defined. The y infinity, the equilibrium equal to the g times x. The g called the x, it is the input variable. G is called the steady state gain or steady state process gain. If the input is instead vary at each constant time t, the input-output relationship can be modeled as follows. The called nu. The nu 0, nu 1, nu 2, nu 3. So pronounced as a total nu. Pronounced as nu. Okay, actually this is a V. Actually, this is a V in not Greek letter, the Rome letters. Okay. This is corresponding to counterpart V in the Rome letter. So this nu 0, nu 0, nu 1, nu 2 are called the impulse response function, called the IRF. Since the nu j may be regarded as the output, the nu is the output to the impulse. So yeah, this nu, yeah. So let me state again. The nu 0, nu 1, nu 2 called the impulse response function. So this is a response function. So corresponding to the may regard as the output to the impulse function. So impulse function is like our impulse. When t is time is equal to 0, then going to be on and off. This is on and off. If t equal to 0 and this variable is on. If t is not equal to 0 and the variable is off. So let me see that. So from here, let me see that when t equal to 0 is on, otherwise it will be off. Let me see that. So this is rationale. The y0 should be 0 when t equal to 0. This is 0, nu 0 times x0, right? X0 when t equal to 0 is on. So xt is 1. So y0 equal to the nu 0. So this is the impulse response function. Remaining, then when x equal to 0, x is x minus 1. Since the t is not equal to 0, x minus 1 is 0, x minus 2 is 0, and so on and so forth. So yt can be represented as a polynomial in terms of the h polynomial in the back-Cauchy operator and times xt. So this is the impulse response function. On or off. Let me say that again. This is the on or off. So it is a feedback control perspective. So let me do that one more time. Y1. Let me say that. If the y1 equal to the nu 0, nu known x1, nu 1 x0, since the t is equal to 1, so the x1 is equal to 0, x0 equal to 1. So y1 equal to the new one, that's equal to the impulse. x1 equal to the new one, x2 equal to the new 2, x3 equal to the new 3, and so on and so forth. So in a feedback control perspective. So let me say that since the chapter 4, there's going to no homework for the chapter 4 since if there's a chapter 4, I'm totally behind the schedule. So I need to finish chapter 6 and chapter 7. So I hope I can cover chapter 6, 7. So chapter 4, I can only quickly review all of them. A quick review of that. Hold on. The first order dynamic process. Suppose that in the process deviation from target obeys the transfer function like that, where observations are taken every 20 minutes. So one observation every 20 minutes. Yeah, let me see the example. Yeah, let me see that steady state. So, okay, see the illustration, figure 4.2. Figure 4.2, the unit impulse response function, x norm, impulse function 1, the new t impulse. So when x equal to 0, x0 equal to 1, the other x9 equal to 0, x equal to, no, when t is not equal to 0 and all the x are zeros. So the xt, and this is the new t called the impulse function, new 0, new 0, new 1, new 2, new 3, new 4, new 5, impulse response function. And this time this equal to this, and this move to the right hand side, move to the right a little bit when t equal to 1. So multiply this, produce this, and then move the xt to the right a little bit when t equal to 2, and this times this produce the third one. Like, okay, this is definition. So this is rationale by considering the figure 4.2, and so we have it. Okay, so this is dynamical system. Look at this. Yeah, quite interesting. The first order dynamic process like this. Okay, the 0.5, the process gain, x2. This is the time delay, k equal to 2. So going to wait 2 period of time until the xt going to have an effect on the output of the yt. So it's called the time lag, or called the time delay. Time delay. Okay, then. Okay, before we do that, and then, okay, we see this example one more time. So where observations are taken every 20 minutes, this can be written in difference equation. Then yt, so multiply this to the left-hand side, yt equal to the 0.2 yt minus 1 plus 0.5 xt minus 2. Then this is a AR, this is an autocorrelation. Suppose that we have a y norm equal to the 0, and that at 0, at that time 0, we introduce a unit impulse. We make the S0 equal to 1 when t equal to 0, and xt equal to 0 when t is not equal to 0, then we have it. So new 0 and bring it to here. And the y1 equal to the 0.2 y1 equal to the 0.2 y0 plus the 0.5 x minus 1. So since t equal to 1, so this is equal to 0. So the y0 equal to the 0, so this is 0, so this is the new one. So y0 new new 0, y1, the y1 new 1 equal to 0. So y2 equal to the 0.2 times the y1 plus the 0.5 x0. Since t equal to 2, x0 equal to 1, so 0.5 times 1 is 0.5. So y1 equal to 0, so y2 equal to the 0.5. So 0.5 is defined as a new 2. So impulse for impulse equal to 0 when t equal to 1. When t equal to 2, the impulse is 0.5, and so on and so forth. Let me do that once again. Y3 equal to the 0.3 times the 0.2 y2 plus the 0.5 x1. Since this t equal to 3, so x1 equal to 0, and the 0.2 times the y2 here is the 0.5. So 0.2 times 0.5 is 0.1. So keep doing that. So when we keep doing that, the deviation from target and the weights converge to 0 when t is starting with 0. So it is an instance of first order dynamical process in which there are 2 time periods of input-output delay, like this. This is time input-output delay. So that is to say the effect of a change in x is first observed after 40 minutes. Since we see that, so going to take that every t minus 2. So going to observe the effect every 2 time period. Each time period accommodate 20 minutes. We're going to wait 40 minutes to see the effect of x on y. So thus y0, y1 equal to 0, and the y2 not equal to, see that? y0 equal to 0, y1 equal to 0 until the leg 1, leg 2. So y0 progressing to y1, progressing to y2, then we have the response of the xt on y. So we need to wait how many legs? Leg 1 and leg 2. Each leg accommodate 20 minutes. So we need to wait 40 minutes to see the effect of xt on yt. So we need to wait minutes. See the x on y. To see the effect of x on y. On y. So let's get back to. So stop here for any question. Pei Zhen, any question? Hello. Pei Zhen, where is Pei Zhen? I do not see Pei Zhen online. Are you there?
Yes.
Okay. Is any question so far?
No.
Okay. John, any question? Why are you leaving? So. Oh, they are leaving. Hold on. Let me wait. Yeah, we wait a minute. Hold on. Let me My student leaving. Hold on, I need to. Yeah. Yeah, would you hold on a minute? I need to contact them. They are leaving. Would you hold on the online a little bit?
Okay.
I need to try to find them. Why they are leaving? Okay. Okay, so. Okay, I think you guys all back, right? Hey, Zen, are you back online?
回来了。
Okay, cool. Okay, thank you. John, are you back?
Yes.
Okay, Shanghai, are you back?
Yeah.
Okay, cool. Then we just review the textbook until right here. Any questions so far?
No.
Okay. If there's no any question, we're going to move on. So going to calculate the stability of the transfer function. So transfer function is stable if IFFF, that means if and only if. This is if and only if. This is called the IFFF. If and only if. Then if the absolute the sum of impulse is less than infinity, so going to have a finite impulse, then the transfer function is stable. The steady state process gain is obtained by fixing all the xt equal to 1 for all the discrete time. So yt equal to the y infinity, then summation starting the j equal to 0 until infinity, the new 0 equal to the g. So y infinity equal to the g times x. So y steady state equal to the steady state gain times x. Steady state times x. Then we're going to review the textbook. Stability. So we move to the section 4.1, this description of the transfer system. So this difference equation form of a transfer function. So yt equal to the, in here, this is a polynomial times a b polynomial. So we move this part to the left-hand side. So this is yt minus a1, yt minus 1 minus a2. And the right-hand side is a b known minus b1 backwash operator minus b2 backwash operator minus 2. The B minus BS backwash operator minus S times xt minus K is K times the system delay, or K is system lag. The K is defined as system delay or system lag. So so this is a polynomial in the order of R, minus 1, 1, 2, 3, 4 until AR. So this is the order of R. This this is the order. This is the order of R in a polynomial. Then this is a little bit weird, strange. Well, yeah, this is the weight of the representing of the style difference. We instead use the minus right here, minus B1, B0 minus B1 minus B2, system lag. This is a 1, this is T minus K minus 1 in here. This is T minus K minus 1. This is T minus K minus S, and so on and so forth. So this is order of S. Backwash operator, this is order S in here. And the B polynomial in the transfer function model. So order of S in the B polynomial transfer function model. Then in here, we still like to factor out the backwash operator K. So we're going to use the backwash operator K, xt. So this is, well, or you directly represent as A times YT equal to B times the xt minus K. K is the system delay. How long we're going to wait? This is the time period of time we need to wait until the xt have an effect on YT. So K is called the system delay. So 4.1 description of the transfer function. Hold on, let me just okay, let's take continuous. Okay, there's a 3 example. The 3 example. Okay, 1 minute. Take this 3. This one, and the continuous medical process of this 2. Okay, so we'll be back in 5 minutes. So please read those examples. The example of transfer function for discrete part and the continuous manufacturing process. So we'll be back in 5 minutes. Please read these 2 pages. Okay, we're back to work. First one. The first one is discrete part manufacturing. Discrete part manufacturing process called the DPM process. So consider first case of discrete part, for example, machining of a metal part. The controllable factor will be typically the machine set point. Yeah, you can say that is a set point or recipe, the dimension. We aim the machine at to perform a cut on the part called the setup point, called the set point. So the dimension, so yeah, we can say that is a set point for specification. This is the set point for specification. Then controllable factor will be typically the set point. Suppose that we change the set point from part to part, whatever setting xt minus 1, yeah, set point we have before producing part number t. So this setting will affect only the part number t. So we're going to have. So before we're going to do the set point setup, so there's a t minus 1 yt observed deviation from target, or you can say actual dimension minus the nominal. So you can, this is target minus the measure as you are. Measurement. So this is target minus measurement. Then this is deviation actual dimension minus nominal. The beta is the process gain, which for the well-calibrated machine, that will be close to the 1.0. So this is beta process gain, close to 1.0. So previous setup equal to the next one. So the process subject to disturbances due primarily to the wearing off in the cutting tool, but also due to the variation in the raw material, thermal effect on machine tooling and other factors. Thus, we actually observe like this. So yt equal to the beta times the xt minus 1 plus disturbance. So the noise and NT will typically follow a low order arrhythmia. As we mentioned, we addressed in chapter 3. So with drift like those described in Appendix 3B. So this transfer function model is known as a pure unit delay. So this is a pure unit delay right here. Or responsive model in which the dynamic behavior of YT series due to only to disturbance dynamics, not to process dynamics. So this is no dynamic relation between the X and Y. So this is the next one. So the previous, so called a deadbeat control. This is pretty like a DEA, deadbeat control. So there's a only called, this is only due to the disturbance dynamics, right here, disturbance dynamic, not to process dynamics. There's a no dynamical relationship between the X and Y. There's only one delay. And continuous manufacturing processes. Okay, we'll stop here. So we're going to have a 10 minutes break, and we're going to return to the continuous manufacturing process after 10 minutes break. Okay, see you soon. Yeah, hold on. Yeah, hold on. I'll be back in a minute. I to fill my water. I'll be back. Okay, we back to work. Yeah, let me see. There's okay, back to work. So continuous manufacturing process, instead of continuous manufacturing process such as a chemical process where the product flow through a series of the pipes and tank, or the multi-step process or sequence, typical controllable factor are temperature, pressure, flow rates, or amounts of certain ingredients that are mixed up in order to achieve desired quality characteristics. The relation between the quality characteristic Y and the controllable factor X will usually be governed by a differential equation that, or regression model, or transfer function model. That model the delays and the inertial element like a pipe tank, etc., of such a manufacturing process. So if X, Y, and X are measured at discrete points in time, the effects of a single change in X at time t will be spread over several subsequent value of Y. So eventually making the Y reach a steady state is going to be stated as follow, like this one. So from here, there's a first order and second order, the A transfer function by either the first order or second order transfer function. So this is the B known, the initial gain. B known and A1 a parameter. B known A1 parameter at the input-output delay, T minus K, in some other process, a second order transfer function, B known. This is the A1, A2, this is the A polynomial. So in either case, YT will be observed in the presence of disturbances due to the raw material change, fluctuating environment conditions, and similar factors. So an REMA disturbance and anything can be added to either of these two models, can add to the plus NT and plus NT to the right-hand side, So yeah, let's move to the slide. Move back to the slide. So this is transfer functional system defines this one for stable system. The transfer system defined as the H polynomial equal to the B polynomial. This is the system delay divided by A. Most of the rule must be outside the unit circle. This to be stable. Steady state gain can be obtained. So xt equal to 1 in this equation, xt equal to 1. So in this equation, the limiting yt when t approaching infinity, just put it back, the b0 minus b1, b2, b3 under bs, divided by 1 minus a1, a2, ar. That is this ratio equal to steady state, steady the process gain. So we also follow identification, estimation, and diagnostic for the model checking. So this is the transfer function example. 4.1 would like to calculate steady state. Like this. Like see this example, 4.2. For the transfer function in this example, we have that if we set up xt equal to 1, this is equal to 1 for periods t, then y infinity equal to 0.2 divided by 1 minus the point. This is the backwash operator. 1 minus a1, 1 minus a1. So 1 minus 0.2 the 0.8. This is 0.625 g is a steady state. There's a long run or asymptotically gain of the process. So know that if I set up, now if I set up the summation starting the j starting 0 to infinity, the impulse function converges to the 0.625. Well, it can be proved for sure. So this implies that transfer function is stable since we have the steady state. The steady state. I think there is a. Do we have a question? Okay. Okay, then we move to the 4.2. This is a little bit complicated. The identification of the transfer function model in RSB. So R is a polynomial. The S is the order of the B. The K is the system delay. So the new J impulse response way are useful to model identification. So this relationship, the B polynomial divided by A polynomial equates to H polynomial form, is useful for model estimation. So yeah, we're going to equate both sides. Equating both sides, the two representation of the H can be equated. Okay, I'm sorry. So that is the polynomial equation. Look at that. Yeah, this is kind of complicated. Let me show you. Yeah, two presentation. Let me see that YT. Let me show you this way. Return to the page 137. This is textbook. The representation H of the Bagorsh operator are equivalent. So YT equal to this one. Then let me show you. Okay, YT equal to this one impulse function, right? New known x1, new 1, xt minus 1, new 2, xt minus 2, and so on and so forth. So this is the YT equal to the H. So this is H. Then in here, where is the H? H is the B divided by is a backwash B and the backwash operator minus Q over A is H, right? So this is the H polynomial. The H polynomial can be equated equal to new the transfer function system. So we do the equation like this. So this is a transfer function model. This is a polynomial function model. So it can be equated from both sides. So we just multiply this to the left hand side to expand all of the terms out. So yeah. So equating coefficient power like in the backwash operator. Yeah, let me see that. So this is like a Diophantine equation. So this is quite complex. Expand and factor out. Yeah, sorry, I need to turn this off. Okay. So expand and factor out for k less than k, j less than k, j equal to k, j k plus 1 plus 2, and j greater than k plus s. That's for different scenarios. So can be found this relationship like this. Yeah, kind of ugly, right? So proceeding this way, we get the following. Yeah, the way are grouped according to the 3 different equations, they obey. Know that in the first group, there are k weights. In the second group, there are s plus 1 weights, k plus 1, k plus 2, k plus s. And the third group, there's an infinite number of weights. So there's 3 different groups. So this is kind of messy. Summary the way of the transfer function model of order RSK formed a 4 group. The first k need to be 0. There's no impulse. First k, no impulse. No impulse. And s plus 1 minus r way follow a no fixed pattern, no particular pattern. Yeah. Second group, particular pattern. Then third one, there's a r way which are starting the 0 like this, a polynomial. Could be, yeah, no, they are starting the value r weight. They are starting the value of the r weight, the a polynomial times mu equal to 0. Then the weights of the new starting the k plus 1 following this one. So it could be exponentially or sinusoidal decay, like a AR. So exponential decay or sinusoidal decay. So this is a first order. So this is second order delay. Okay. So let me see some example. Yes, this is kind of ugly. Since it's very difficult for me. So typically I going to write that, write those equation on the board. So for me, this is very difficult. So I'm gonna skip that. I'm gonna skip all of that since we cannot go to the class. Typically, I use a choke to derive every cases for you. Yeah, see, hold on. Give me a minute. I get to my water. Yeah. So I strongly hope the pandemic can finish very soon. Then, yeah, since for me it's very difficult to lecture, especially for this for this particular material, which cover very important concepts. So, okay. So I'm gonna skip that since I cannot continue since it's very difficult also. So I'm gonna skip the explanation of this table, which is going to be quite, well, if you do not convey the research on the control, so it can be negligible. Okay, we move on to the 4.2.1. Okay, so I have to, otherwise, yeah, I cannot. Yeah, identification, okay. So I skip that, okay, then. Okay, move to the slide, page 17. The transfer function with added noise is this, added noises. So disturbance RXD normally enter the system and are not controllable. So Box and Jenkins proposed to add a noiser that follow ARMA PDQ model transfer function. So this transfer function added the noise. The noise follow the ARMA model as well. So the transfer function, okay. First one, this transfer function plus added noises. So like this, which can be represented as a block diagram, xt minus k coming to the b over a. xt come into the b over a and producing the signal, and into this symbol is summation. Operator. This is a summation operator. Then producing the then this is st and signal nt. This is nt. Nt represent as a c over d times the epsilon t. So this is c over d, and the white noise come into the c over d, producing the disturbance. So let me see. The white noise comes into the polynomial c over d to generate the disturbance. Yeah, that's what I mean. So the yt, the b over a times xt minus k plus the c over d times epsilon t. So in here, d may have a one or more root on the unit circle. In this way, we obtain the model known in the control engineering literature as the Box and Jenkins model. So if it is exactly under on that unit circle, so there's a difference equation. Yeah. Then let me back to the slide. And identification of the transfer function model. Under noise is present, so identification based on the time impulse response function is feasible only if the noise level is low. Otherwise, so the noise is present. However, it cannot be inferential. So this is key. So let me type it. Noise is present, but not differential. Okay, this is key. So assume in control engineer. So if the noise is too high, how can we deal with that? That's quite straightforward. If the noise level is too high, hold on. Yeah, somebody has been kicked out. Question? Okay. So if the noise level is too high, then the process engineer need to use the filter to screen out the noise first. Use a filter to screen out those noises to let the process only subject to the inference of the Y sequence as possible, as Y as possible. So to define after difference the series D times. The cross variance at leg K is defined like this. This is the gamma XY. This is called the cross correlation, cross covariance or cross correlation. Yeah, could be the cross correlation or cross variance. So, however, since the XY, the gamma XYJ is gamma YX minus J. So we only need to compute one of them. This is called the even function. So when we change that the even function, the cross correlation between the X and Y is a rho. The gamma divided by the sigma X and sigma Y. That's like a cross correlation, the correlation function between two variables. However, the rho XYJ is not equal to the YXJ, since the function, the cross correlation not symmetric around the 0 point and off function. So we do that from the X to YJ and the Y to X minus J. So it is reverse order. So let me see how this is the off function. This is not even function. It is off function. Not of the even type. So cross correlation is an off function, not of even type. Yeah. Let me see the illustration right here. Okay, take a look at that. 1 minute. Figure 4.4. One minute. Okay, then back to the figure 4.4, the cross covariance function, the YT and XT. So Y, X, and Y the row x and yj not equal to the y2xj. So that is to say, this is the gamma x and y coming this way. To the lower left to the upper right. So going to progressing the k period ahead from the t to t plus k, right? Then, so this is from the x to y, and y2x is t plus k from the gamma y xk. So from the y t to xt plus k. So actually, from second one is from the upper left to the lower right. The first one from the lower left, upper right. Actually, they are crossing, so they're totally different. Totally different. Okay. So from the equations 4.7, the gamma xyk, gamma yx, so the meaning. So gamma xyj not equal to the gamma yxj. So these are crossing, they totally different. So things are, they are crossed. So the gamma xy is accusing, is not equal to gamma, I'm sorry, see that? Since they are crossed, so gamma xy is not equal to the gamma yx, since they are ODD function. Hold on. They are all function. So this is the question, show why they are different. J, this is different. And if we do that, xyj equal to the yx minus j. Xyj, hold on, let me show you yxj, yxj, doing this way equal to from the upper left to the lower right, that's equal to from the lower right to the upper left. So going this way and going that way going to be equal. So gamma xyj equal to gamma yx minus j, they are equal. Okay, yeah. So since they are not equal, since cross correlation is not symmetric around the zero, it's an odd function. So this is the estimate of the gamma and the rho, like this one. Okay. So this estimation of the rho and gamma, if n pair observation xy are available, then C is used to estimate gamma. The R is used to estimate rho. Okay. So likewise, if x and y, xt and yt are not cross-correlated, then can be shown, the Barlet in shown in the 1955. So it two time series not cross-correlated, and one of them is a Y sequence, possibly due to pre-whiting the input. So what is a pre-whiten? Pre-whiten, that's we call pre-whiten. Pre-whitening, that means we're going to center the data. Center the data, and we need to scale the center data to have unit variance. Okay, we call the pre-whitening. Then, well, the variance of the sample auto cross correlation can be approximate. Standard deviation of that could be approximated by the square root of the 1 over n minus j. Yeah. The j starting 1, 0, 0, 1, 2, 3. It depends on what is the time lag being discussed. So identification of the transfer function model. So we mentioned if the cross correlation varies around 0 with the standard deviation like this one. So if xt and yt are not cross correlated, one it must be white. So this and this. So yt equal to this one. Then in here, the nt, the disturbance is represent or in the form of c over d times c over d polynomial times epsilon t right here. So the epsilon t. So apparently the correlation within series will mask the correlation between series, since we have two series, xt and yt. Let me see that. So we have now two SERI, two series, xt and yt. So don't get yourself confused too much. So well, now we have two series, so that's why the cross covariance and the cross correlation are required. Since there are two series in understudy together, it is why the cross correlation is investigated. Okay. Then I know this is not easy to comprehend the first time, so I hope that's why I truly recommend you guys to print out the textbook. That's always try to urge you to print out the text. Apparently the correlation within series will mask. So going to veil the correlation between series. It makes sense. It makes sense to make one of two series white, maybe one of them, such a procedure called pre-whitening. Whitening, yeah, let me put on here. Enter the data and the scale, the center data to have unit variance. That's called the pre-whitening. Like a PCA, right? Have you ever heard PCA before? Yes, I think you do. Like PCA, the principal component analysis like a PCA, pre-whitening. So pre-whitening for identification transfer function. So input itself have autocorrelation. Input itself xt have autocorrelation. Pre-whitening is good to find or build or detect the relationship between xt and yt. So correlation within its series marks the correlation between them. So okay, so. Yeah, let me move to the textbook. Okay, like this, pre-whitening for identification of transfer function, page 145. Like this. we're going to pre-white xt into the A over C to produce an alpha t, which is y, like A alpha C alpha. So pre-whiteling, we'll put alpha. So xt is stationary. We can build an ARMA model for it of form where alpha is y sequence. So from going to do the A over C, that is apply on xt to let xt become alpha t, which is y. And we also apply A over C polynomial on yt. It won't matter. It doesn't matter if the beta t is y or not. It won't matter. Only one of the two sequences is white. So A alpha over C alpha yt equal to beta t, like this. A over C yt B A backwash operator system delay A alpha C alpha xt and L alpha C alpha disturbance. That's it. So we do one more additional filter. That's called the filtering. That's pretty. Yeah, like the way we perform filtering. Yeah, does it make sense? I think it makes sense to you requiring. So once we do that, since we move to the toggle to here. Yeah, it's a little bit complicated, right? Okay, move back to the slide. Then since xt has been pre-whitened, since we difference d times, so we can build an ARMA model for that xt. So differences d times. Then the A alpha xt has been difference. C alpha t. So we use the A and the C to do the filtering. This A alpha over C alpha perform filtering to let the xt turning into alpha t. Alpha t is a y sequence. That. Then it's a y noises, and A over C, a filter apply the beta t to produce the beta t, yt to produce the beta t. It won't matter beta t is a y or not. Apply the same filter to that, so transfer function turn out to be this way. I mentioned this already. So multiply both sides by alpha t minus j. This is alpha right here. Oh, alpha t minus j cross correlation. Then taking expectation yields. Yeah, blah, 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 like this. So we're doing the transfer function. This alpha representing x, the beta representing y. However, they have been filtered by A alpha over C alpha. So we take the autocovariance, to find out. So if the transfer function model, we would like to have an estimated impulse response to use the identify RSB like this. So this is obtained. So we can do the, this is a disturbance that it defines the difference between the observable output minus forecast. This is estimate transfer function times xt, or a rational transfer function model has been estimated. So sample autocorrelation function and the sample partial autocorrelation function of NT disturbances are used to identify an ARIMA PDQ noise model for that. It's like this. This is noise model. This is a noise model. So then we like to, hold on, okay, that. The offline estimation transfer model, once RSB and PDQ has been identified, then corresponding parameters are accessible, A, B, C, D. AC is for the A is for AR, B is the transfer function, C is moving average, D is for the polynomial for the noise variable. So which can A, B, C, D? How can right here in here? I would like to show you where's A, B, C, D. Let me see that. Hold on. Yeah, I would like to get the A, B, C, D. Yeah, wait a minute, let me find the equation. I would like to have an equation right here. This is A, this is B, this is a C, and this is D. The A polynomial for YT, B polynomial for the X, C and D is D and C is the ARMA for the disturbance. Okay, let's see. Let's moving on like that. Okay, so okay, like this, we like to estimate those unknown parameters. So need to estimate by minima corresponding sum square A, B, C, D, given the B being the initial value of X known, initial value of the Y known, and the epsilon. Just hold on. So it is a good approximation of the maximum likelihood estimator. If you can see that is the arrow following the normal distribution for sure. So yeah, this is by minimum conditional sum square. This is a good approximation for the maximum likelihood. To avoid transient effect of the initial value, we start adding term. Adding turn on that. So ABC with the mark across 63 using the nonlinear least square we mentioned in the first hour of the class. So when we estimating RSB, it's not a major problem. Instead, we would like to identify RSB properly. So estimation is not it is not a thing. It is not an important method at all for us. Then. Okay, so finish 4.2. I stop here. 4.2.3. Well, we're going to 4.2. So 4.3. Let me see that. 4.2. So we have done this one. 4.2.2, I'm sorry. It's 4.2, 4.2, 4.2. Okay. So I stop here next. No, the day after tomorrow, Wednesday, we're going to start at 4.2.3, starting right here. Starting from here. Right here. What is that? I cannot find out. Hold on. Okay, there's an example. I cannot find that. Hold on. Give me a minute. Offline. Okay, we're going to start the example 4.3. 4.3. Okay, I see you Wednesday. And also, I'd like to give you a reminder. Remember to send your homework to the email by Wednesday. Okay, I see you Wednesday. Thank you for your cooperation to attend the online class. I know it is not that used to be, and do not feel used to be. Do not used to be it, and I hope you can get used to that later. I tried my best, try as clear, has a clear representation as possible in the online class. I hope. I ask for your understanding, so I see you soon. Okay. Remind Pei Zhen to record my lecturing and finally send the file to me. I'm going to upload to the YouTube. I'm going to share to the iSchool through the personal portal to the NTUT system. Is there any question so far, guys, ladies and gentlemen? Any question?
Professor.
Yes.
No.
Hello. No? Is
No.
any question? No. Okay. I see you Wednesday. Remember submit your homework and prepare the examination of next week, covering chapter 1 to chapter 3. See you soon. Bye-bye.
Thank you.